In this video, we'll work through several practice problems on binding energy, mass defect, and the strong nuclear force to help strengthen your understanding of these concepts. To get the most out of this practice, pause the video at each question and try to solve it on your own before viewing the solutions. Then resume the video and compare your answers with the explanations provided. Good luck, and let's begin. Here's the first question. Calculate the mass defect of a helium-4 nucleus. Mass of proton, neutron, and the actual mass of the nucleus are given. So take a minute, pause this video, work through this problem by yourself, and then come back and see how we answered this question. So in order to answer this question, we first need to figure out the number of protons and neutrons inside the helium-4 nucleus. There are 2 protons and 2 neutrons inside the helium-4 nucleus, and the formula for mass defect is the sum of the masses of individual or free protons and neutrons minus the actual measured mass of the nucleus. So we need to multiply the mass of protons, which we have 2, by the number or the mass that we are given. So we need to multiply 2 times 1.6726 times 10 to the minus 24 grams. That equals a value of 3.3452 times 10 to the minus 24 grams. This value equals the total mass of protons, free protons. Then we need to multiply the mass of neutrons by 2 because there are 2 neutrons inside the helium-4 nucleus. So we have to multiply 2 times 1.6749 times 10 to the minus 24 grams. And we get a value of 3.3498 times 10 to the minus 24. This is the total mass of free neutrons. Since helium-4 nucleus is composed of 2 neutrons and 2 protons, we need to add the total masses of free protons and neutrons that we just obtained. After we do that, after we sum the 2 masses of free protons and neutrons, we get a value of 6.695 times 10 to the minus 24 grams. This is the total mass of free protons and neutrons. The equation for mass defect requires that we subtract the actual measured mass of the nucleus from the sum of the free protons and neutrons. When we do that, when we subtract the two numbers from one another, we get a final answer of 0.049 times 10 to the minus 24 grams. This is the mass defect. And as you can see, the actual measured mass of a helium-4 nucleus is not the same as the sum of free protons and neutrons. Once protons and neutrons come together to form the nucleus, some energy is lost. And this energy loss translates into a loss of mass according to E equals mc squared formula, or the Einstein's formula. Binding energy and mass are directly proportional to one another. So a loss of energy due to the binding of free protons and neutrons translates into a loss of mass. Let's work on another problem to see how we can calculate the mass defect and also this time the binding energy as well. So number 2 reads, calculate the mass defect of lithium-7 in kilograms. What is the binding energy per nucleon in lithium-7 in joules? The mass of protons and neutrons are given. The measured mass of the lithium-7 nucleus is also given. Take a minute, pause this video, work through this problem by yourself, then come back and see the solution to this problem. So here's the solution to this problem. And in order for us to figure out the answer to this problem, we need to find the number of protons and neutrons in the lithium-7 nucleus. The number of protons inside the lithium-7 nucleus is 3. So we have 3 protons and 4 neutrons. We then need to figure out the sum of the masses of 3 protons and neutrons. In order to do that, we need to figure out the combined masses of the 3 protons and the 4 neutrons. So once we multiply 3 by 1.6726 times 10 to the minus 24 kilogram, we get a value of 5.01786 times 10 to the minus 27. This is the total mass of free protons. Then we need to multiply 4 because we have 4 neutrons inside the lithium-4 nucleus. We need to multiply 4 by 1.67493 times 10 to the minus 27 kilogram. Once we do that, we get a value of 6.69972 times 10 to the minus 24 kilogram. This is the total mass of free neutrons. Once we add the total mass of free neutrons to the total mass of free protons, we get a value of 1.1758 times 10 to the minus 26 kilogram. Then we need to plug this number into the mass defect equation. So we need to subtract the actual mass of the nucleus from the mass of the sum of the free protons and neutrons. Once we subtract these two values from one another, we get a value of 0.007758 times 10 to the minus 26 kilogram. This value is the mass defect, or the difference between the sum of masses of free protons and neutrons minus the actual measured mass of the nucleus. The second part of this question asks for the binding energy of lithium-7 nucleus. So to answer this question, we need to use the E equals mc squared formula. E is the binding energy in joules, m is the mass defect, and c is the speed of light. So E is equal to 0.007758 times 10 to the minus 26 kilogram times 3 times 10 to the 8 meters per second. And you have to square that value because the equation requires that you square the c value, or the speed of light. If we plug this into our calculator, we get a value of 6.98 times 10 to the minus 12 joules for binding energy. If you are asked to calculate the binding energy per nucleon, you simply need to divide the binding energy above by the number of nucleons, which in this case, for the lithium-7 nucleus, there are 7 nucleons. Nucleons are the number of protons and neutrons. Once we divide our binding energy by 7, we get a value of 9.97 times 10 to the minus 13 joules per nucleon. And this answers number 2. Number 2, it asks the binding energy per nucleon for each of the following nuclei is given. Which of the following atomic nuclei is the most stable? The binding energies are given in MeV. This stands for mega electron volts. Mega electron volts are just another unit of energy. Just like how joules is a unit of energy, mega electron volts is also another unit of energy. So this question is asking for the most stable nucleus. Which one do you think is the most stable nucleus? Take a minute and think about this question. So here's the answer to this question. We said before that a higher binding energy means that more energy is released when protons and neutrons come together. And if more energy is released when protons and neutrons bind, this means that the nucleons are held more tightly in the nucleus, which makes the nucleus more stable. So we need to look for an answer choice with a higher binding energy per nucleon. K39 has a binding energy of 8.55 mega electron volts per nucleon. So K39 is the most stable out of all the other options. So answer choice B is the correct answer. Question number 3. The binding energies per nucleon of some of the elements are listed below. Which of the following has a smaller mass defect? These values are given in mega electron volts per nucleon, so the binding energy of each nucleon is given, but the question asks for the smaller mass defect. Which one do you think has the smallest mass defect? Here's the answer to this question. Binding energy and mass defect are related to one another by the formula E equals mc squared. Binding energy and mass defect are directly proportional to one another. This question is looking for the atomic nuclei with the smallest mass defect. An element with a smaller mass defect would need to have a smaller binding energy per nucleon. So the smallest binding energy per nucleon out of all the options that are listed is BE9. So that is answer choice A. So answer choice A is the correct answer. Number 4. The mass defect values for the atomic nuclei of the following elements are listed below. What fundamental force is responsible for the mass defect observed in these nuclei? So now you are given mass defect values and you're asked about which force is responsible for the mass defect. Which one do you think is responsible for the mass defect? So the solution to this problem is C. Here's the reason why. Recall that mass defect is equal to the mass of free nucleons minus the mass of the actual nucleus. This missing mass corresponds to the binding energy that holds the nucleons, which are protons and neutrons, together. The force that is responsible for holding protons and neutrons bound in the nucleus is the strong nuclear force. Option answer choice A and B, they represent the same force. The electrostatic force is the Coulombic force, and this force causes protons to repel one another. It does not hold the nucleus together. The weak nuclear force, which is option answer choice D, is responsible for radioactive decay. It is not responsible for binding. So the correct answer to this question is C, which is the strong nuclear force. Question number 5. The mass defect values for the atomic nuclei of the following elements are listed below. Which of the following has the greatest difference in mass between its corresponding free nucleons and the actual nuclear mass? So we are given mass defect values and asked to find the greatest difference in mass between the corresponding free nucleons and the actual nuclear mass. Which one do you think is the correct answer? Take a minute, pause this video, think about it, and then come back and see the solution. So this question is basically asking you which of the following atomic nuclei has the greatest mass defect. The mass defect values are given, and we are only asked to pick the option with the highest mass defect value. So option number C, answer choice C, is the correct answer because it has the highest mass defect value. Number 6. Which of the following best describes the role of the strong nuclear force? A. It prevents electrons from falling into the nucleus. B. It binds protons inside the nucleus. C. It counteracts the electrostatic repulsion between protons. D says both B and C. E is all of the above. Which one do you think is the correct answer choice? So let's go through each answer choice and see which one is correct and which one is not correct. Answer choice A. It says it prevents electrons from falling into the nucleus. The circular path of electrons, the quantized energy levels, and the Heisenberg uncertainty principles, they are responsible to explain how electrons do not collapse into the nucleus. So answer choice A is not correct. It's false. Option B. It says it binds protons inside the nucleus. Option B is correct because the strong nuclear force explains how both protons and neutrons bind to form the nucleus. Option C. It says the strong nuclear force counteracts the electrostatic repulsion between protons. This answer choice is also correct because without the strong nuclear force, protons would repel one another and they would fly out of the nucleus. So both options B and C are correct, which makes answer choice D the correct answer. And here's the solution, a full explanation to question number 6. So answer choice D is the correct answer. After completing these practice questions, if you would like to take the next step and work through an MCAT-style passage, you can click on the next video or find the link in the description below. If you would like to review the concepts or watch the full version of this lesson, which includes the complete concept review, guided practice problems, and an MCAT-style passage walkthrough, you can access it through the links in the description or by clicking the videos shown on the screen. Thank you for watching and keep practicing. You're much closer to your target MCAT score than you might think. Good luck on your MCAT journey and see you on the next one.